Hi. So last time we derived a couple of differential equations that are satisfied by the electric field and the magnetic field. And if you look at the derivations from last time more carefully, um, what you should realize that we extend the differential equations to the case where there is a time-dependent magnetic field, but we never really extended the situation where there would be a time-dependent electric field. And I mentioned that there would be a modification to these differential equations once you take into consideration the time dependence of the electric field as well, but I haven't really gotten around to showing you exactly what the consequence of that time dependence is. So here I want to begin by describing exactly what gets changed in the differential equations that we derived previously. And to that end, we have to go back to the equation for the curl of the magnetic field. So I hope you recall that the curl of the magnetic field can be written after some vector manipulations that can be written in this way as basically the current density plus something, and that extra bit was shown to be 0 in the previous lecture due to the fact that there is a certain current conservation law that has to be satisfied. But you should also recall that the manipulation rested heavily on the assumption of time-independent situation, so-called the steady state, where the continuity equation reduces to the divergence of the current density vector being equal to 0. And therefore, we could argue that this thing in the integrand vanishes identically, and therefore the divergence of the vector potential vanishes identically. But this is not always the case. In the general case, of course, there is no reason why this time fluctuation of the charge density should always be 0. So let's allow that to be non-zero and just see what the consequence would be. Instead of taking this quantity, the divergence of the current density vector, to be 0, we can take it to be the minus of the time derivative of the charge density function. Okay, so this is a new expression, which is non-zero. But again, this time dependence can be taken outside of the integral because there's no other term in these integral that would depend on time explicitly. So we can take it outside the integral like this. And the expression inside is precisely what we used to call the scalar potential. Okay, and therefore, the divergence of the vector potential equals now some time derivative of the scalar potential multiplied by some constant. Okay, previously this time dependence was 0 because we were always looking at the steady state charge distribution, for which of course there would be no time dependence in the electrostatic potential. But if the charges are fluctuating, then there's no reason why the scalar potential should not fluctuate together. Okay, so this is simply a statement of the more general situation of where charges are fluctuating. And if you take the divergence of this, the gradient of this quantity further, then obviously the operations of time derivative and space derivative can be interchanged. So this expression ends up being equal to the time derivative of the electric field. okay, multiplied by some constant. So overall, the more correct equation becomes the sum of the current density and some new funny expression that would involve the time derivative of the electric field. Okay, so this is it. So it wasn't that hard to generalize the old situation to the new situation. And luckily, this turns out to be the complete answer. This is sometimes known as the displacement current. This is the theoretical invention of Maxwell when he worked on the theory of electricity and magnetism. And by introducing the existence of this extra term, he was able to really unify the electric phenomena and magnetic phenomena in terms of a tightly coupled set of equations, and also be able to derive the so-called wave equation of electromagnetism. Okay. So when Maxwell introduced this term, he called this the displacement current. And I think the reason for that is that you can combine these two terms by after taking out the overall factor of permeability, mu zero, as the physical current density, J, plus some extra current density, JD. And JD is nothing but this time derivative of the electric field. So there's not necessarily a charge that oscillates in its place, but it's really the electric field itself that's oscillating, but somehow that takes on the character of the current density vector. Okay, so the interpretation is, honestly speaking, rather vague, but the mathematics is not that confusing. Actually, it's quite simple, as we have just shown. So this is the full description of the behavior of the curl of the magnetic field, and this equation remains true down to the relativistic regime and survives the special theory of relativity and so on. Okay, now we are going to go into the more thorough discussion of the individual pieces of the electromagnetic phenomena, starting with the electrostatics. And I'm going to introduce to you a bunch of concepts and results that are rather rigorous. And it's good to know that some of the things are entirely possible, but other things are entirely impossible in electrostatics. And I want to give you some of these examples and demonstrate their validity through some mathematical manipulation. The first statement that I want to prove to you is the fact that no charge can move itself. So what I mean by that is if a charge is out there somewhere, then it creates electric field. And electric field acts on other charge and push or pull that piece of charge through Coulomb force. So you may very well imagine that a charge can exert a force on itself, because charge is both the source of electric field, but also it is the recipient of the electric force. But here the statement is that such thing can never happen, and there's no charge that can sort of put a force on itself and move spontaneously. And the proof goes roughly as follows. Let's say we're given some distribution of charge described by this function rho. Rho gives you the charge density at a given point r in space. And with such a charge distribution, there would be an electric field distribution given by this integral formula. This is nothing but a statement of Coulomb's law. And if this electric field acts on a second object consisting of its own charge distribution, and to distinguish this from the first object's charge distribution, I'm going to call this mu. The force acting on the second object will be given by the integral of the charge density multiplied by the electric field integrated over all the regions of space that the second object occupies. Now I can combine this formula with the first formula giving rise to the electric field due to the first object, and the combination would result in this sort of expression. So if you can somehow manage to pull off finishing up this integral by integrating these functions both over r and r prime, then you would be able to calculate the force that this first object consisting of the charge distribution rho exert on this second object consisting of the charge distribution mu. However, if there were only one charge object, then by necessity this second charge distribution has to equal the first charge distribution, and therefore this force law reduces to, actually this is typo, I should have written rho of r multiplied by rho of r prime divided by the distance cubed multiplied by the displacement vector r minus r prime. However, it's easy to see without even picking up a pencil that this integral has to be zero. By symmetry, basically. Because this entire term that I label as 1 is actually symmetric under the interchange of the two particle coordinates. After correcting for the typo and relabel this as rho, this is rho r times rho r prime, which under the interchange of the particle labels becomes the same as it was before. And likewise, this r minus r prime becomes minus that after the interchange, but since we're only talking about the magnitude, the value remains exactly the same. So this is a symmetric portion of the integral. However, there's an anti-symmetric portion, which is r minus r prime, which obviously changes sign under the interchange of the two particle labels. So if you have one symmetric function and one anti-symmetric function and has to integrate over both coordinates, the result is, by symmetry, always a zero. Okay. So even if you have a very, very tightly confined distribution of charge, still such an object cannot spontaneously push itself into a certain direction. It's just, such possibility is just ruled out by the argument that I have just given. And exactly the same argument applies for gravitational force, like the Earth exerts gravitational force on itself, but that doesn't mean that the Earth can spontaneously push itself into a certain direction. Only other planets and stars can exert force on the Earth and affect the motion of the Earth. Okay, and another noteworthy thing about the nature of the electric field is that under the static situation, the electric field is the gradient of some scalar function, which I used to call the electrostatic potential. And instead of labeling it with V, I'm going to label it with the Greek letter phi simply because our textbook happens to use that symbol to denote the electrostatic potential. So in keeping with the notation in the textbook, I'm going to use the gradient of phi with a minus sign as the electric field. And using this property, one can easily show that if some charged particle whose charge is q moves through space from position r1 to position r2, then the work done by the electric field on this particle as the particle moves from r1 to r2 depends entirely on the values of the electrostatic potential at these two endpoints. And the proof is really trivial once you know the standard results of vector calculus, that what gets involved is the integral of the gradient of some function along a line, and such line integral ends up being the difference of the values at its two endpoints. So it doesn't matter which trajectory is being followed by the particle's motion, as long as the start point and the end points are the same. Then the work involved in moving the particle from position R1 to position R2 is entirely the same. Okay, but of course this substitution of the gradient of the potential for the electric field only works if the entire situation is time independent, and this substitution no longer applies when things become time dependent. But then under the time dependent situation, we don't really have an energy conservation law at work, so it doesn't really make sense to talk about energy in the first place, let alone the conservation of energy. Okay, so we're still in the safe haven for that matter. Okay, another interesting piece of theorem or exact result in electrostatics is something called the Earnshaw's theorem. Earnshaw's theorem doesn't get talked about too much in maybe undergraduate curriculum, but it's a pretty useful thing to know, especially if you're an experimentalist and trying to play around with various rules of electrostatics to improve the operation qualities of the machine you're building and so on. So it's one of the theorems that simply cannot be circumvented. So no matter how carefully you make your apparatus, there's no way you can make it so good that it violates Earnshaw's theorem. Okay, so the statement is that if you have a vacuum, which is completely free of any electrostatic charge, then inside a certain region enclosed by the surface, which I label S, the potential may have a maximum value or minimum value somewhere, but the maximum or the minimum can never occur inside the region. If it occurs at all, then it has to occur somewhere on the surface. Okay, so the statement of the theorem itself sounds pretty deep maybe, but once you take a look at the proof, you realize that this is not such a deep theorem. Rather, the nature of the theorem is pretty simple and almost trivial. So to present the proof, first imagine the contrary situation. So this is an example of a proof by a contradiction by starting out with a contrary situation and develop some logic, you arrive at the conclusion that contradicts your original assumption. Therefore, the original assumption had to have been wrong. So I'm going to imagine the contrary and say that the potential reaches a minimum value at some position, let me call that R minimum, and that R minimum is located well inside the surface. Okay, so then by the very definition of this function being at a minimum, no matter which way you move away from this minimum position, the potential, the value of the potential can only increase. Okay, that's essentially the definition of some function being at a minimum. Okay, so using the vector language or vector calculus language, what that means is that the gradient of the potential inner producted with the direction vector. So this is the direction along which you're moving away from the position of the minimum potential. So here I have drawn this dot as the location of our minimum, and various arrows indicate possible different choices of the n vector. So this inner product can only be positive if this point happen to give the minimum value of this potential function. Okay, now let's explore the consequence of that statement. The consequence would be that this integral covering the entire surface surrounding the minimum point has to be positive, because at every single patch of the surface, this integrand has to be a positive number. So if you integrate a whole bunch of positive numbers, the result is necessarily some positive number. But this integral also happens to be excuse me, happens to be nothing but the surface integral of the electric field. So this integral basically measures electric flux that are penetrating through this imaginary sphere that surrounds the R minimum. And by Gauss theorem, that surface integral measuring the total electric flux also happens to equal the total charge inside that surface divided by some number. But didn't we start by assuming that there's no charge inside this entire surface? Right? That was the very assumption that we began with when we started to think about this statement. And therefore, we have arrived at a contradiction, which means there's no way you can create a absolute potential minimum or a potential maximum for that matter in the region where there's no charge. Okay, a more colloquial and a practical way of putting this statement is that there's no way to completely trap a charge by purely electrostatic means. Okay, so if you can create an electrostatic potential that looks like that in all the directions, you have a potential trap in the x direction, potential trap in the y direction, potential trap in the z direction, then you can put the charge in the middle of such a trap, and the charge will never go anywhere but stay trapped in that region. But that's essentially impossible due to the theorem that we have just proven. So in order to trap a charge, you have to do something a lot more clever than using electrodes and capacitors and so on to create an elaborate scheme of the electric field. Because no matter how elaborate you try to be, there's no way you can beat Earnshaw's theorem and create a potential minimum in the vacuum. All right, so now we move to the next important theme in electrostatics. That's, of course, Gauss' law. The Gauss law, in its integral form, states that the electric flux through some closed surface has to equal the total charge inside that surface divided by some number. And this law, as a calculation tool, becomes very powerful when the situation has some symmetry in it. And a good example, as we know, is the situation where the distribution of charge has some spherical symmetry. So here I denote with a shade some spherically shaped ball with some charge inside. And I'm going to assume that the charge density is purely a function of the distance from the center of the ball, but not on the orientation. And as such, the entire geometric situation will possess a spherical symmetry. And in that situation, the electric field should also be only pointing in the radial direction, which means that I can easily claim the consequence of this performing this integral to be the electric field strength at the distance r simply multiplied by the surface area of the sphere, which is 4 pi r squared. And that equals the total charge that's encapsulated within the radius of r divided by the dielectric constant. And therefore, the electric field strength at the distance r from the charge center equals the total charge enclosed within the radius of r divided by the r squared. So this looks quite a bit like Coulomb's law, but the difference is that as you move away from the center, so as you vary r, there's a possibility that this charge also varies, because it's possible that as you move out, you get to enclose more and more charge inside the sphere. But no matter where you're putting your meter stick and measure r, the electric field is always given by this simple and quite universal formula. And you can see that Coulomb's law is just a special case of this, where Q of R becomes just a constant. Okay. There's also a useful application for situations that possess cylindrical symmetry. For example, if you have a cylinder with some charge distribution inside, and let's say the charge density is uniform along the length of the cylinder, and also uniform with respect to the angle. However, the charge density may well depend on the distance, on the radial distance from the origin, which I wrote as rho. Okay. Well, in this case, applying Gauss' law, the left-hand side of the Gauss law pertaining to the electric flux becomes this electric field strength at the distance rho multiplied by the surface area, but the surface area of a cylindrical shape is basically the circumference of the circle multiplied by the height of the cylinder. So I can call this 2 pi rho where rho stands for the distance, and h is the height of the cylinder. Then this whole thing equals the charge that are trapped up to the distance of rho divided by the electric constant. So again, dividing by this geometric factor, you arrive at the electric field strength that falls off as inverse law and inverse of the distance, and scales with the linear charge density, which I wrote as lambda. So this definition of linear charge density is simply the total charge enclosed by the cylinder out to the radius rho divided by the height of the cylinder. So this is the amount of charge per unit length along the height of the cylinder. Okay, and of course another well-known and perhaps final application of the power of Gauss law in computing the electric field is the situation where you have this infinite slab of electric charge distribution. So although here I have drawn it as a finite width slab, in fact it extends out to an infinite distance in this way, and also extends out to an infinite distance in this direction, and only the thickness remains finite. And in that situation, the electric field can only have z component, and that's the component perpendicular to the plane. And here you can apply the Gauss law and work out the electric flux as essentially twice the electric field strength multiplied by the area of the Gaussian surface, which then equals the total charge that's enclosed by this thing that I've drawn in dotted lines. So again, by dividing by the geometric factor, you arrive at this pretty familiar expression for the electric field being entirely proportional to the surface charge density. Okay. So this is a surface charge density or areal charge density given by the total charge divided by the area, by the cross-sectional area. Okay. So those are a quick summary of the application of Gauss law in calculating electric field in the blink of an eye for a certain class of highly symmetric situation for charge distribution, and how I hope you guys are able to jog your memory about these things. Okay, so that's it for this lecture. Thank you.